So our next chapter is on equilibrium. And there's two quintessential things to do with equilibrium. One is, given an equilibrium constant, be able to calculate final concentrations given an initial concentration. The other is this example problem behind me, perhaps, where given an initial concentration and a equilibrium concentration, calculate the other species concentrations and calculate an equilibrium constant. So consider the following reaction. I got A, which goes into B and C, and there's the stoichiometry of it. And here's our equilibrium arrows, meaning the reaction is dynamic. There's always product turning into reactants. There's always reactants turning into products. And then an equilibrium constant might give us the balance between those two. So here's how we're going to want to tackle this. I'm going to write the equation right here, and I'm going to write the word initial. So we take a tenth of mole and we put it in a 1 liter flask, and so molarity and moles are going to be the same. We want it to be really simple molar concentration, and I'm going to use K sub C to delineate that. So it says a tenth of a mole is initially put in there. So how much B and C do you think we have initially, right at the beginning? Yeah, there can't be any, so I get to put a 0 in there. All right, and then it says A was allowed to react, so that causes a change. So the first thing we might figure out is some A disappears, so I'm going to put a minus sign. Some B appears, and some C appears. So I'm going to focus on B for a second, and I'm going to say, I don't know how much B forms, and when we don't know how much something forms is, what's our favorite variable?
X.
X. So I'm going to say X amount of B forms. All right, so if B is X, what is C going to be? 3X. Very good, and likewise, this thing here has to be what?
Minus. No.
Minus an X, but what's the coefficient? 2X. All right, so this is the change that happens. It's dictated by that stoichiometry, and then we're going to say at equilibrium, how much A is going to be there?
0.2.
How about 0.1 minus 2X? All right, now we do know this value right here, but this is what I tell students. Always do the bottom row of your ICE table symbolically. Why do I call this an ICE table? Look, that's a I-C-E. That kind of spells ice. So it's going to be X and 3X. And right, we know what this equals. That equals 0.02 molar. Now what do I get to do? I get to solve for X. So far, so good? So far, so good? All right, now I'm going to divide both sides by 2. So what's half of 0.08?
0.04.
Right, all right. Now we know what X equals. This also equals, well, this is going to equal the concentration of B, right? So we've now found the concentration of B to be, and the concentration of C is going to be 3 times that. 3 times 4 is 12. And we know the concentration of A because it was given. So for this particular reaction, this equilibrium constant based on concentration, we'll see in the slides here in a little bit, is equal to the products raised to the coefficients divided by the reactants raised to any coefficient. So it looks like I'm going to have a concentration of B, concentration of C. So given an initial concentration and an equilibrium concentration, calculate the other concentrations of the species. Once you do that, you can calculate an equilibrium constant. Equilibrium constants are unitless. So the answer to that question is so when your car burns fuel, it sucks in lots of nitrogen because the atmosphere is about 80% nitrogen, and inside the engine's real hot, and you form some oxides of nitrogen, and there is a bunch. So this one is N2O4, and it's clear and doesn't have any color. And so if you start out with some of this, it'll react and turn into NO2, which is brown. And how many of you, when you drive down to Colorado and you leave Cheyenne, and what's the first thing you might see?
The smog.
The brown cloud. And then today with the forest fire, you can see a lot of brown in the sky. So this is what's responsible for that brown cloud. Chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. That's why we do the kinetics before the equilibrium. At the beginning, this is rushing over to the product. And as soon as some product forms, it can react and become reacted. But when these rates are equal, we say equilibrium has been established. And so here is a rate expression for NO2 turning into N2O4. Here's a rate expression for N2O4. And you can see initially if we start out with just the N2O4, we're going to have some rate, whatever nature gives us, rate slowing down because the concentration of the species is slowing down. And this, as soon as we start to form some, rate can increase. And here we've reached a time when the forward rate and the reverse rate and the reaction are equal. Now if we look at the concentration of these two things, we start out with just all N2O4. That means there's no NO2. This concentration starts dropping and dropping, and the concentration of our product starts building up and building up. And then eventually we reach a point where the concentrations are no longer changing. We say once equilibrium is achieved or established, the amount of each reactant and product remain constant. And so here is an equilibrium constant, and it's given by this equation here. And you can see it has the forward and reverse rate constants. So here's the forward reaction, here's the rate law, here's the reverse reaction, there's the rate law. This is just an FYI. At equilibrium, the forward rate and the reverse rate have to become equal. And then we see this ratio of the rate constants. But what's really better is this ratio of products over reactants. So these are gases. So here's some partial pressures. And here we're starting with just all N2O4. And here's an experiment where we're starting with all NO2. And then nature does its thing. And here are equilibrium pressures. And if you're really bored and want some excitement, take this number and square it, and then divide by that number, and you'll get this number here. Take this number, square it, and divide by this number, and you'll get that number there. And that's plugging in those concentrations into this rate expression. So we can possibly do an experiment, measure these concentrations, and if we plug them into this expression, we see we get a constant. And that is the equilibrium constant, and it tells us the balance between reactants and products at equilibrium. So here is a generic reaction. A and B react to form C and D. And the lowercase letters represent the stoichiometric coefficients in the balanced chemical equation. And this thing is known as the law of mass action. The equilibrium expression for this thing, and C stands for concentration. Notice it's products, C and D, each raised to the corresponding coefficients, whatever we find there. And in the denominator, the reactants, so whatever coefficient we find in front of A here, we're going to raise the concentration of A to that coefficient. Whatever coefficient in front of B we find, we're going to raise B to that thing. Just like we did here. There's a 2 in front of A, so I squared A. Coefficient of 1, I raised that to the 1 power. Coefficient of 3, raise that to the 3rd power. Now my example problem, I could have said these were all gases, and then I could have put in partial pressures, and the process would be the same, because pressure is proportional to concentration, and we can write an equilibrium expression like this. And notice we have the same thing. It would be the partial pressure of C raised to the power of the coefficient we find in front of product C, partial pressure of D raised to whatever coefficient we find in the balanced chemical equation in front of species D. Same thing here with my reactants A and B. Whatever coefficients are found, raise that to the power. So this is the one you want to look at and realize this is the way nature works. So if you have some balanced chemical equation in front of you, you can write the equilibrium constant expression by putting products over reactants raised to the powers of the stoichiometric coefficients you find in front of those species. So I like to work a lot just in the concentration with moles or molarity, or strictly with gases and partial pressures. But there's a difference between them. Well, sometimes and not always. There you go, love that. So here is an equilibrium constant based on concentration, and here is one based on pressure. So pressure in a gas, we might as well pull out the ideal gas equation. PV equals nRT. If I divide both sides by V, I get moles over volume. What does that remind you of? Moles per volume.
Molarity.
Yes, molarity. And if we plug that into our expression for case of P for each substance, we get this relationship here. My equilibrium constant based on partial pressures is equal to the equilibrium constant based on concentration times RT raised to the delta N. What is the change in N? Moles of gaseous product minus moles of gaseous reactant. So when we have some magical situation where these are equal, what does the change in N become? 0, and that's kind of nice. And then an equilibrium constant based on pressure and based on concentration are the same. Many times that's not the case. Most of the times it's somewhat different. And so here's how you can convert from one to the other. Most of the problems we're going to look at, we're just dealing with one or the other. So what does that equilibrium constant tell us? Well, if it's really large, like much greater than 1, that says the reaction is product favored. We have more product at equilibrium than reactant. And so here's kind of a nice cartoon drawing. This is a bigger shape than this shape here. So if we have an equilibrium constant of 20, or 2.5 times 10 to the third, or even 8, we might say 8 is much bigger than 1, and we say equilibrium lies to the right, more products. Now some equilibrium constants have very small numbers, like 4.5 times 10 to the negative fifth, or 6, or even lower. That'd be a number much smaller than 1. Then we say the reaction is reactant favored, or reactant predominates at equilibrium. So once again, this cartoon drawing, this is a bigger shape than this one here, telling us that at equilibrium there's more reactants hanging around than products. And for fun, I'm going to just look here at our 0.02. B was 0.04. C. We'll just make these molarities. And looks like we have, looks like we're close to 1. So we don't have any double inequality situations there. Probably should have chosen one that had a larger equilibrium constant. So given a chemical reaction and an equilibrium constant, we want to be able to manipulate the chemical equations and ask ourselves, what effect does that have on the equilibrium constant? So our first example we looked at with the brown cloud and the clear cloud that's just as deadly to breathe in as this one here. This is what we first looked at going this way. So at a given temperature, these are always for a given temperature. Temperature can affect the equilibrium constant, and you know that from thermodynamics. That should make sense. We'll explore that in detail towards the end of this chapter. So notice that if I have this constant and it describes the balance between these two species, if I write this in the reverse order, nature still has the same balance, but something has happened here. Notice up top I got n2 squared because it's a product. When I flip the equation around and now it becomes a reactant, it ends up in the denominator, not the numerator. And what was in the denominator comes up to the numerator. So if I got this flask at equilibrium sitting in front of me, the concentrations don't change when I write it one direction or the other. So what property might we say we have when we take a quotient and flip it? Reciprocal. Right, so pull out your calculator and go 0.21, hit the reciprocal key, or go 1 divided by 0.221, and what do you think? Help me with my live presentation.
Wouldn't it be the opposite?
You're going to get like 4.72. Or if you take 1 divided by 4.72, you're going to get 0.211. We say the equilibrium constant of a reaction that has been multiplied by a number now is going to be the equilibrium constant raised to that power. So here's our original equation we looked at. Now for whatever reason I multiply by 2. There's a 1 here, so this becomes a 2. 2 times 2 is 4. And once again, if I imagine I got this flask in front of me that's at equilibrium, the concentrations are what they are. They are what they are. But now, due to our convention, this law of mass action, we got to raise this to the 4th power, raise this to the 2nd power, and we can see mathematically it's probably going to take this answer and square it. So flipping things around, we have the reciprocal relationship. Multiplying by a number, we're going to raise the equilibrium constant to that number. Why would we want to do such crazy things? Well, sometimes we might have an equilibrium process that is really a function of a couple different things going on. Here's kind of a good example of that. H2S in aqueous solution can give us a hydrogen ion and hydrogen sulfide. So this is foreshadowing of acid-base reactions. And this is the only type of equilibrium arrow I could find in PowerPoint. It means this double arrow like we see there. And here's the equilibrium constant. So at equilibrium, do we have more reactant or product at equilibrium? Yeah, more reactant. So here, my example here of 0.1728, that's not very far away from 1 in either direction. Really can't tell what's going on, especially with all the cubes squared. All right, well, we might say this is like a diprotic acid. We can start with HS minus and pull off another proton in solution, leaving us with sulfide in solution. And here is the equilibrium expression for that. So I can sum these two equations. If I did sum these two equations, I'd have this bottom equation. We might say to ourselves, well, what is our K here? It says it's the product, so if I multiply these two together, and you can see a very small equilibrium constant. So here's hydrogen fluoride giving the proton fluoride. There's the equilibrium constant for this reaction. Here looks like oxalic acid giving me 2 protons and an oxalate ion. And here's the equilibrium constant with that. We could ask ourselves, what is the Ka for this? Well, notice this first part of this looks like the first part of this. So I'd probably write this one as is. And then notice here I have oxalate and there I have oxalate. I think you were onto something. I think I would flip this one around. So I think I'd square this one and multiply it by the reciprocal of this one. We will test that out next time we meet. So we'll call that a day.